got the description of a Ka, and now we move from a Ka to a pKa. A pKa is simply the minus log of the Ka. It's a number that is more easily understood to look at it in a table or a list of numbers. The smaller the number, the stronger the acid. So if I said this has a pKa of 20, okay, approximately equal to 20, would you say that that's an acid or a base? It's a very strong base, in fact. This indicates that with such a high pKa that this is a very basic species and a significantly strong base. Okay. Now, what do we do with these pKa's or Ka values once we have them? We can determine something about an equilibrium, or at least make a conjecture as to which side the equilibrium lies in a given reaction. So let's say I take let's take ethanol. I think I could have a pKa for ethanol sometime. I don't really need to have a pKa for this one. I'm just going to write these as equal arrows for right now. Let's do something that's a fairly strong base. Plus H2O. Let's do a base first. Okay. This is an alcohol, and I'm putting it with a strong base. An alcohol, would you consider an alcohol just by looking at it? Would you consider it a strong acid? No. Why? Because you should have learned what the strong acids were a long time ago in 1210 and 1220, right? There's a certain list of them, and that list, outside of that list, everything else is considered weak of some sort, right? So we have H2SO4, HCl, HBr, HI, so forth. They all belong to that strong HNO3 strong family. So this one we know is weak, so it's got to be either a weak acid or weak base or both, okay? What if it's both acidic and basic? What do we call that situation? Like water. Amphiprotic. But it has both basic and acidic characteristics to it. So in this case, I'm going to put it in with a strong base. So we know that this one's strong, because it's a group 1A metal with an OH minus, so we know it's a strong base. So if I react these two together, I'm going to get this as far as one of the products, and then water will be the other product. Okay? Now, to which side is the equilibrium line? We're not going to include the spectator ion, which is the potassium line. You can put that out here as a potassium. We know it's going to somehow be associated with the water or with the negative charge of the alkoxide here. But I'll just leave it like that for right now and just kind of ignore the spectator ion. Okay? So in this case, where I'm adding an alcohol with a strong base, to which side does this equilibrium lie? Okay? One of the ways in which you can determine to which side this equilibrium lies, we have to see where the strengths lie. We have a strong base over here. If this were to go backwards, which is the base and which is the acid? In other words, the back reaction, which is the conjugate base and which is the acid? So this is the conjugate base, and this is the conjugate acid, right? Let's take a look now at the relative strengths of these things. If I have a ethanol, you probably have a pKa of this thing. I have methanol, probably pretty close to methanol. Let's say that it's around methanol, so it's about 15.5 is the pKa of ethanol. Probably very close to that. Okay, so let's say it's around 15.5. What is the, and then we look at the pKa of water. The pKa of water is 15.7. Okay. What does that tell us about the equilibrium in this particular case?
Close.
Pretty even.
It's pretty close. Okay? So this would have a significant equilibrium, arrows going forward and back. What it's telling me, I don't have the strength of the alcohol on this side and the strength of the acid on this side as far as acid strengths are about the same. So there's not one of these pushing. The conjugate base, so if this has a certain pKa, this has a certain pKb, this has a certain pKa, this has a certain pKb, we know that they're related to each other, but if these are closely related, then their pKbs are also closely related to each other. So this would tell me that this has a significant both forward and back arrow, this particular reaction. Okay? Let's take another situation now. We take something like, let's see if I get another reaction here. This one over HCN, I think it's HCN. Let's take HCN plus, this is one in your book, I'm just pulling it out here, plus NaOCH3. And I'm just going to write them equal for right now, not knowing which way I'm going. Okay. If I look at this and I look at these two species here, which one's the acid and which one's the base to begin with? So if I say this is an acid-base reaction, which one's the acid and which one's the base?
The base has the Na salt, right?
The base has the salt. So remember that group 1A metals associated with a conjugate base of some species. Now can we recognize that as being a conjugate base of something? Could that be the conjugate base? If I replace that with a hydrogen, would it be an alcohol? So it's the conjugate base of an alcohol. In other words, this is a sodium plus OCH3 negative, right? So when they write it like this, I could write it like that and say, now I kind of understand what it is. The sodium is a spectator ion, so I'm going to just kind of not look at that for a minute. Does this have any hydrogen to donate? Well, not really from carbon. Remember carbon? Hydrogens are not acidic, not very acidic at all. There has to be very special situations for that to occur. So we're thinking that this is probably the acidic hydrogen right here. Okay? And that this can be donated over to this species right here. So now I can write the product, which would be HOCH3 plus C dot dot N minus, there's also a pair of electrons on here. Okay. Now I look at this and I say, okay, to which side does the equilibrium lie, or is this another one of those ones that's fairly equal? Okay, or is it heavy to one side or the other? So let's look at the relative strengths of the acids. Here's the acid on this side, and this is its conjugate base, right? This is the acid on this side, and this is its conjugate base over here. So I'm going to put base, acid, acid, base. Right? Hold on, I got some important calls. Sorry, I have to have this on for right now. I got important phone calls coming in. Right, so A, B, A, B. Now, if I take the hydrogen and I transfer it over here, then this is the conjugate acid. So I look up on the table. You're not required to memorize pKa values. Alright, that's not something that I require you to memorize. But if I give you a pKa, you should know how to use it, okay? So we look up for HCN, we see that the pKa for HCN is 9.22. So it's not very acidic. And then I'm going to look up the methyl alcohol, the acid over here, and this is on page 25, by the way, your table. This one is 15.5. Okay? So now I'm looking at this and I say, okay, which one's the stronger acid out of these two? This one's a stronger acid. Okay? Now it's a stronger acid, and it's not just by a little bit, because the pKa, just like the pH scale, is a logarithmic scale. So for every point down it becomes 10-fold stronger acid. So this is a much stronger acid than this is, right? Can you get that? Because I've now dropped down almost 6 pH units, or 6 pKa units. Okay, so this is a much stronger acid. So what does that tell me about the conjugate base? The stronger acid will have a weaker conjugate base. This one will have a stronger conjugate base, right? So I just put weaker and stronger over here. And so I have stronger and stronger on this side of the equation, weaker and weaker on this side of the equation. So at equilibrium, can I make a conjecture as to which way the arrow should be really? Should one be heavier than the other, pointing in which direction? At equilibrium, this one will be shifted significantly to the right, and then this one will be a much smaller arrow back. So I would say that this is right shifted at equilibrium. It lies heavier to products. And you say, now why is this important? This is very, very important as we get into chemical reactions. Because let's say I throw this into a chemical reaction and I want this to be the reactive species. But I put this in as my solvent. What's going to happen between my solvent and this guy? It's going to convert it to this, and this may not be nearly as reactive as the alkoxide form, and I may have just destroyed my reactant in this acid-base reaction. So it becomes very, very important later on in chemistry that we understand something about these different types of acidity and basicity, and to which side an equilibrium would lie. Now, if this is what I want as my chemical reactant, then would this be a good mix? If I want this to go on to some other reaction, I say, oh yeah, this might be a very good mix because this will produce lots of this, and now I can get that reaction and make it move forward. Okay? Does that make sense? So you need to know how to do this. First of all, you have to identify which is the acid and base. That might be the hardest part. Once you decide which is the acid and the base, then you just take your proton, move it over, write the two products. Once you have your two products, decide which one's conjugate acid, which one's conjugate base. Then look at the two acids and their pKa's. Compare the two pKa's, see which one's stronger. Compare the two bases now, because you know the stronger acid is going to have the weaker base. Okay. So does this make sense? Does anyone have any questions on this? You have lots of questions right here. Here's a bunch right here for you to work. If you don't know the pKa's of these, you can look them up on a table. If the table's not readily available, you can look them up on the internet or so forth. I don't expect you to memorize pKa values. You notice I don't ever reference the pKb because I don't really need to. As long as I know what the pKa is, I know the pKb is related to that, but I can make some conjectures just based upon the pKa. Does that make sense? So now you take a look at these two. What happens when you react these two together? Okay, what happens when I react these two together? What happens? Well, that's the one we just did. What happens when I react these two together? Or this? Now, what is this right here? That's an interesting one.
Can we do that one?
Yeah? Let's take a look at it. CH3COO minus.
Isn't that the conjugate base on acetic acid?
Yeah, it's a conjugate basis. So that's one where I said you might have trouble just identifying it at the very beginning. So if I have CH3COO minus plus CH3OH, what they did is they left something off here. What did they leave off? They left have some sort of counter ion, that this came in as some sort of salt. Okay, now, is this an acidic salt, or is it a basic salt, or is it a neutral salt? Well, I have to say, I'll scratch my head and say, where does this come from? The COO, what does it look like it should have been if I would have replaced the hydrogen here? CH3, COOH, and this is, you said that this looks like it's acetic acid, right? So this came from acetic acid, the species right here. But it looks like the conjugate base of acetic acid. So now when I put this in with an alcohol, what's going to happen? So I'm just going to draw equal arrows to start with. See, okay. In this case, this doesn't have a proton to give. The only proton to give is not the ones attached to the carbon, but the ones attached to the oxygen. So I could say from the alcohol, we could possibly get this moving over to here, right? So I'm just going to write it. Even if the equilibrium doesn't favor it, I'm still going to write it as a product. So I'm going to write CH3, COOH plus CH3O minus. Now I'm going to look up the pKa's for the methyl alcohol. That was one we already looked up, was 15.5. Now I'm going to look up for acetic acid. It's 4.76, by the way. It should be anyway. It says 4.74. Most articles reference acetic acid about 4.76, but that's okay. Doesn't matter. Now I look at this. Which one of these? So this is my acid on this side. This is my acid on this side. This is my base on this side. This is my base on this side. I'm not making any, I'm not jumping to any conclusion as to which direction this reaction is going. I'm just looking and saying I have an acid and a base on this side, I have an acid and a base on this side. Now I make some conclusions based upon which one's stronger. This is stronger, right? And I'm comparing it to this acid. Okay, so this one's stronger than this one. So what does that mean about its conjugate base compared to this conjugate base? So this is a stronger conjugate base than this one is a weaker one. And so I have weaker on this side of the equation, stronger and stronger on this side of the equation, so I'm going to get rid of some of that upper arrow and I'm going to say this equilibrium actually lies to the left. So what I have written as reactants are actually favored in this type of situation. Okay? So if I'm trying to get this reaction to go forward, it's not going to go forward. Okay? I'm looking out in the wrong direction. I really should have put these two together.
So I know how you determined the CH3CH, COOH is stronger, but how did you determine that base over there?
A stronger acid has a weaker conjugate base. Then this one is a weaker acid, must have a stronger conjugate base. Right?
Yeah.
So it's just based upon the weakness of this acid means its conjugate form is stronger. It's a fairly strong acid. Okay? Or a strong base, I want to say. Any other questions? Does that clarify it for everyone in the back? You guys are just kind of hanging back. You good? Okay. Alright, that's going to be very, very important throughout the entire semester. Very, 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 very important. Entire semester. Work on those problems. Okay. Now, let's talk about a different situation. It's not too much different. Let's say I generate CH3O minus in a chemical reaction, and I have mixed in here. I have something else, which is this is one out of your book, by the way. I'm just going to show this one. I have a CHHHCl. Okay. And I mix these two together. Interestingly enough, there's a type of acid-base reaction that can take place even if you don't transfer a proton. We call this a Lewis acid-base situation. Okay? So we're going to talk about Lewis acids and bases. Does anyone remember the definition of a Lewis acid or Lewis base back from 1210 or 1220?
Does it transfer electrons?
It does, has to do with electrons. So which one is the acid?
It's that non-bonded electrons.
Good. So the acceptor of unshared electrons is the acid. The base then must be the donor of unshared electrons. So I look at these two and I say these two react with each other. Can you tell me just by looking at them which one might be the Lewis acid and which one might be the Lewis base?
The base is gonna be the CH3.
So I heard somebody say that this is the base. Do you all agree with that? Why?
Because it has unshared electrons.
This one doesn't have any unshared electrons unless you look out here in the chlorine. You say, okay, there is a possibility out there in the chlorine. But if I say the reactive center is actually the carbon and not the chlorine, then you say there's no unshared on the chlorine to be given. Okay? So this is the base, this is the Lewis acid. Okay? In organic nomenclature terms that we use, the vernacular of an organic chemist, we call these guys right here, we call these a nucleophile. This is the base, by the way. We call those a nucleophile because they are seeking out a nucleus to interact with. These we call the in other words, these are nucleus-loving species, these are electron-loving species. So the electrophile is the acid, the nucleophile is the base. Okay? We draw this as electron-pushing arrows showing the reaction is that a pair of electrons comes in and seeks out a nucleus, and the nucleus that it seeks out is this carbon nucleus. And so we point right at that carbon center. What happens during this reaction is a pair of electrons is broken, and this is what we call a homolytic, heterolytic cleavage, where both electrons go to one species. It's called a heterolytic cleavage. Lytic refers to breaking or lysis, splitting. Hetero meaning that it's an unequal splitting. The electrons are going to just one species. So we draw that, we take an arrow, and we draw just a little looping arrow right onto the chlorine itself, saying that that pair of electrons is now being dumped onto the chlorine. Okay. So in this reaction, what we get is a CH3, O, C, H, 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 plus CO minus. So this guy actually attached that carbon and split off this chloride ion in this reaction, and this would be a Lewis acid-base reaction. Okay? Where this is the nucleophile. We also call this a nucleophilic substitution reaction. Nucleophilic substitution. Why do we call it a nucleophilic? Because it involved a nucleophile seeking out an electrophile, and what happened, it attached to the carbon and displaced the chlorine, so it actually substituted for it. So it's a nucleophilic substitution. It took its place. Okay? Make sense?
So in those reactions, is that always going to take place where it's going to push one of them off?
It's going to push some sort of group off. In a nucleophilic substitution reaction, something's coming off and being substituted by another species.
So what would be an electrophilic reaction then?
What?
What would be an electrophilic reaction then? If that's a nucleophilic, right?
Okay. An electrophilic reaction involves this one right here. So I think I've got an example. Okay. Yeah, this will work. Now, this is a different type. This is not a substitution reaction. It's called an electrophilic addition reaction. So this is an addition, not a substitution. But it is electrophilic. Okay? How does this thing work? Is we believe it works the following this is the electron pair donor right here, this extra pair of electrons. The hydrogen ion is an acceptor. So in terms of a hydrogen ion, an H+, remember HBr is acidic, it's both a Lewis acid and it is a Bronsted-Lowry acid, H+, because it doesn't have electrons to give, but it's seeking electrons. Okay, so it's an acid in both definitions. Alright, so this is seeking out a pair of electrons, it comes over here and finds a pair of electrons, so this is an electrophilic addition reaction, where now this comes out and seeks this pair right here. So in this case, we draw the arrows coming from the electrons towards the nucleus. Okay? Now this actually goes through an intermediate, and so it becomes a little bit harder to define, but the intermediate looks like this. Because this pair of electrons was pulled away from this carbon, associated with this hydrogen came in here. You notice it didn't substitute anything, it didn't push anything off, it just added to the molecule, that's why it's called addition reaction. Then this species right here undergoes a reaction with the Br minus that's left behind, so you have the Br dot 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 minus, and this comes down here, a pair of electrons, and associates with this species right here, in forming this guy right here. Okay? So this is an electrophilic type of addition reaction. Okay? Most important thing is I just want you to understand these electron pushing arrows and that these reactions take place where electrons are seeking out nuclei that are electron deficient. Remember that a carbocation, this guy right here, is electron deficient.
Is there another product?
Oh, sorry, I forgot. This should have a CH3, I'm sorry, CH3. That should be different, I'm sorry. This is actually the major product. Kind of interesting. We'll talk more about this reaction later on. It follows a rule known as Markovnikov rule.
How did you know that hydrogen was the acceptor? I thought that hydrogen can only have like 2 pairs of electrons attached to it. That long.
Hydrogen can come off as an H+, right?
Yeah.
That's just a proton, and a proton does not have a pair of electrons, it has no electrons. So it cannot be a Lewis base at all. So it has to seek out electrons. So this is the Lewis base, this is the Lewis acid. Okay? Does that make sense? Okay, so H+ is always a Lewis acid. There is a form of hydrogen that is a Lewis base. What would be the form of hydrogen that's a Lewis base? You ever heard of a hydride? A hydride ion, an H dot dot minus. These exist as well. This would always be a Lewis base. This is always a Lewis acid. I think you guys can work the homework from there. It shouldn't be too hard. You should be able to figure it out from there. If not, come up and see me. Or Ryan will go over this and
4:30 today.
we'll go over this again to get another dose of it. Let's move on to chapter 2. Chapter 2, I've actually covered some of chapter 2. Okay, one thing we're going to learn about now is something that you should have picked up in 1210 or 1220, and it's something that I put out there for you to review, is hybridization. And hybridization for organic chemistry is a little bit easier actually than inorganic chemistry because we don't worry about d orbitals. We only worry about S and P hybridization. So there are only 3 forms of hybridization for organic chemists that we're mostly involved with. That is your sp hybridization, your sp2 sp2 hybridization and your sp3 hybridization. Now what does sp2, sp3 actually mean? Let's go back and review real quick. Let's take a carbon atom, for example, and look at its outer valence shell. So if I have a carbon atom, its outer valence shell is the second energy level. It has a 2s and a 2p sublevel, right? And I draw each of the orbitals as a line, representing the degenerate orbitals. You can put them as a circle or a square, it doesn't matter, right? We know that the p orbitals are a little bit higher energy than the s orbital. S usually fills first. Okay, so if we look at a carbon atom, we place the electrons according to Hund's rule, the Pauli exclusion principle, we get something like this, right? What this shows us is that there's two unshared electrons in the valence shell for carbon. If you look at one of the simplest forms of carbon out in nature, it is actually CH4. That means there are actually 4 hydrogens attached to a carbon. If the hydrogens, what does the valence shell of a hydrogen look like? It has 1 electron in an s sublevel, right? So it's bringing in 1 electron into the Lewis dot structure, right? So 4 hydrogens are bringing in how many electrons? 4. How do we overlap 4 electrons in here? How do those, does 1 hydrogen donate 2 electrons to 1 orbit in a p orbital? Because there's only 2 unshared electrons in a carbon atom. This didn't make sense to Linus Pauling, who won a Nobel Prize for his proposal that this doesn't make sense. You have 4 hydrogens each bringing an electron. You only have 2 unpaired electrons. How do you get 4 hydrogen atoms pairing up with those? With that 1 carbon atom. And so he came up with a hypothesis that said that maybe the s orbital mixes during the reaction with the p orbitals and forms a new orbital called a hybrid orbital. Okay? This hybrid orbital is a mixture of s and p orbitals. Okay? In this case, we are going to mix 1 s orbital with all 3 p orbitals. Okay, so here's the s, here's the p. If we mix these together, what happens if I mix 1 with 3 p orbitals? And just mold them all together in a big lump of clay and then say, okay, something's got to come out of this. You're going to get 4 total hybrid orbitals coming out of this. They're going to be somewhere between the s energy and the p energy. So they're going to be somewhere in between these. But I'm no longer going to have an s, and I'm no longer going to have individual p's, but now I'm going to have 1, 2, 3, 4 hybrid sp orbitals. So these are sp hybrids. To distinguish that it involved all 3 p orbitals and not just one of them, we call it an sp3 hybridization. Now let's put in the electrons from carbon using the Pauli exclusion principle. I get 1, 2, 3, 4 electrons. Now can we explain a hydrogen overlapping this, a hydrogen overlapping here, a hydrogen overlapping here, and a hydrogen overlapping here, each bringing in their 1 electron to pair with that situation. This makes sense to Linus Pauling, it makes sense to other chemists, so we believe that this is actually what's happening. What happens when you have these sp3 lobes, the s orbital gets sucked right into the p orbitals and you get these whole new orbitals. They look a lot like a p orbital, but they have s characteristics. So you get one sticking in one direction, but it has a little tiny blob on the backside of it. So now it looks like s and p. But what happens, that's only one of these, so what happened to the other one? Well, it's overlapping too, and it's got a little one there, and then you got another one over here, and then you have another one out here out front, with this little sticking behind there. Each one of these has 1 electron in it, somewhere. Most of the electron density is where? Not in that little tiny lobe in the backside, right? Most of the electron density is calculated to be out in this big lobe. So one hydrogen atom can overlap here with its electron and pair up. So here's a hydrogen. Another hydrogen can pair up right here. Another hydrogen can pair up here. And another hydrogen can pair up here. According to what is known as Vesper theory, Valence shell electron repulsion theory. Should be hard for you, but, what would we predict for how far these lobes are spaced apart from each other? Are they close together, or are they far apart they can get from each other? They're as far as they can get. And so if you have 4 giant balloons tied together, what is the natural geometry that 4 balloons are going to take that they can get as far apart from each other as possible? A tetrahedral geometry. So we know that CH4 is actually CH, H, H, H. Where this is what we call a perspective diagram, where this bar coming out from the hydrogen is projected out of the paper at you. These 2 lines are in the paper, and the one that's dashed going away is one that's back in the paper going away from you. Okay, so that's called a perspective diagram. Trying to give you a 3-dimensional field in a 2-dimensional space, that's all we can do. What we know is that this species looks something like this in reality. Well, we know that the hydrogen atoms are much closer, they're sticking right close to the carbon, so this is actually exaggerated as well, but we have this tetrahedron, a very symmetrical species. Okay? What happens if we change the hybridization to sp2 or sp3? With an sp2, what happens? You're mixing one s with 2 atomic p orbitals, so 3 of them are going to be mixed, but one of them is going to be left behind, so we have an atomic p orbital left behind. So how many hybrid orbitals will we have? 3. Whenever you mix orbitals, you cannot lose orbitals. The total number of orbitals involved in the mixture have to result in the hybrid. So I have 1, 2, 3 sp hybrids. Now to distinguish them from sp3, we call them sp2. And then what do we have left over? An atomic p orbital is still left over. Okay? This atomic p orbital can be involved in unique situations. Okay? These first type of bonds that are formed from overlap of carbons or overlaps of electrons, where they come in head to head, are called sigma bonds. Sometimes we use the Greek sigma symbol. All hybrid orbitals can be involved with sigma bonds. This p orbital can be involved with a new type of bond that we call a pi bond, or you can use the Greek symbol as well, a pi bond. What happens if we have one s with one of the p orbitals? So this is an sp2 situation. What happens if we have one s with just one of the p orbitals? Mix these 2 together. We're going to have 2 sp hybridized orbitals, right? And to distinguish those, we're just going to call them sp, because it only involves one of each. So we have one of each, but what do we have left over? 2 p atomic orbitals. So how many pi bonds can be formed? For each p atomic orbital left over, you can form an additional pi bond. So this has the potential of forming 2 pi bonds. Okay? And it has the potential of forming sigma bonds as well. 2 sigma bonds, 2 pi bonds. This one can form 3 sigma bonds with 1 pi bond. Now what the heck is a sigma bond and a pi bond? Have you ever seen how we draw this, double bond it to this, to this, to this, to this, to this? Okay. What is this second bond right here? We have 2 unshared, or we have 2 shared pairs of electrons. The first one is the sigma, the second one is called a pi bond. How do pi bonds form? Okay. Well, what we have here is a situation where this pink guy right here, think of this is kind of a weird term. Don't think of the pink as being atoms. think of this as being the lone atomic p orbital, and that here are the sp hybrid orbitals from an sp2 hybridization, okay? So this one's sp2 hybridized, this one's sp2, and for sp2 I have 3 sp2 orbitals, right? How do they get as far apart from each other as possible? It's actually in trigonal planar space. Because I also have this atomic p orbital that's influencing this, and this atomic p orbital is saying, okay, stay away from me as well. So I have to push those down. Okay. Now as this carbon atom that's also sp2 forms that first sigma bond, we now have the ability for the two lone atomic p orbitals to side by side interact with each other and form that new type of bond. So it's only one bond, but it involves both the top and bottom lobe. But it's only one pair of electrons. So we now form this bond that we call a pi bond. So this is the sigma bond, and this bond right here is known as the, both the top and the bottom is just one bond. Electron density here and here. We don't completely understand, it's just the way the thing behaves. Okay? This right here has electron density both top and bottom, but it's just one pair of electrons. Okay, and that's formed a pi bond. This pi bond gives characteristics to the overall molecule. It kind of locks it into place. You notice now we can't rotate much. Okay? If I did not have this pi bond, then we could take around that sigma bond, we could do what? We could rotate it. This is how the vision in your eye works. Okay? There's a molecule in there known as 11-cis retinal. 11-cis retinal has a pi bond. When a given wavelength of light comes in here, it actually breaks the pi bond but leaves the sigma bond intact. It breaks it. The molecule rotates out of that position into this position and then reforms its pi bond. But that sends a chemical signal to your brain that has a photon of light has just been received, just by that simple rotation. Let's go on to the SP situation. If you have an SP, you have, I'm going to use this one now as a model. We have, now think of the purple as being the second p atomic orbitals, and the pink ones being the first p atomic orbitals left over. Here's the sp hybrid in here that's forming the sigma bond between the two carbon atoms. But now these two pink ones can be, oh, I'm breaking bonds here. These two can be side to side, but also these two can now overlap. So now I can form a carbon-carbon 1, 2, 3 bond. So that's a carbon-carbon triple bond. What is the natural geometry around this species? Because we really can't see these orbitals right here. So it would look to us as a linear type geometry. Okay? What would be the geometry around this species? Because we really can't see the p orbital overlapping, but we see the rest of this, so I'm going to pull this off. Breaking more bonds here. So we can't see it, but we know that this molecule's got to grease them up a little bit. Where did I break my sigma bond now? Okay, so the P, we can't see this bond up here because it's just a pair of electrons, right? But we can actually see the atoms. So what do we notice about the geometry around each of these carbon atoms? That carbon atom right there. It's trigonal planar. What about that carbon atom right there? It's trigonal planar, right? So this overall molecule looks fairly flat, right? And this is how it behaves. It behaves like a flat planar structure. Okay, with the hydrogens in the same plane as the carbon atoms. Right? Alright. Now, this goes back to our AX notation. Do you remember the AX notation? Negative?
Yes.
X is the number of species attached to a central carbon, or a central atom we just call A. So if we have two species, or just one species attached to a central carbon atom, its only geometry is linear, right? Just have two atoms there, right? What if I have something that's like AX2? that means that I have some sort of central atom attached with two other species right there, right? Okay. This is what we call a group 2. A group 2 situation. What if I have A X to E? What does the E represent? Remember this from Gen Chem? An unshared pair of electrons. Okay, so if I have unshared pair of electrons, so now I have a case where I have two things with an unshared pair of electrons out there, so it's something like this. I'm just going to go A, X, X with an unshared pair of electrons. What is its geometry and so forth? What if I have an A, X to E 2? What does that mean? That means I have some central atom that has attached to X and X with two unshared pair of electrons. Okay? This is actually what we call a group 4. This is a group 3. In the group 3 there are several ways, or group 4, let's work our way back. Group 4 can have 3 different ways of putting these together. I can have an A, X, 4. Right? What's an AX4? It's an A with X, 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 X. What is its hybridization? For organic chemistry, if you have 4 different groups around a central atom, it has to be sp3. So this would have to be sp3 hybridization. Okay. What if I have an A, X, 3, E? That would be A, X, 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 dot, dot. What is its geometry? It's trigonopyramidal. It's like just taking off one of these groups right up here, but leaving the electrons. Leaving the electrons, I can't see the electrons, but they're still there in orbit, so these still stay down in this position, or at least close to that position, so they call this trigonopyramidal, right? So the AX3E is trigonopyramidal. What's the other situation here? AX2E2. Once you get to AX2E2, what is the geometry behind an AX2E2? So if I can start with my tetrahedral geometry first, and I pull off one atom, 2 atoms, and I have 2 unshared paired electrons, that means that this is angular or bent. Okay? You need to review that stuff. Very, very important. I give you a paper, download that. Review the group 1, the group 2, the group 3, and group 4.
Would group 3 be